Hey, alright. So that task completed. I think it's been about 15 minutes. Long enough for me to eat some breakfast. We're going to reconnect and look at how many spectrograms we actually created. It'd be nice to see actually per... Let's look at this real quick. We're going to look at how many spectrograms we have per bird. Let's see. Yeah, we're just going to go through the data directory here. Spectrograms. One for the index, and then look at star.spectro, S-P-E-C-T-R-O. There we go. Dot format, and include that index. There. And then here, the count for that index is equal to the length of that glob. And then one more thing that we want to do before we print this out. Let's see, let's just print it out as a sorted dict. Sorted. Let's see. Sorted by items. So that makes our key is equal to lambda x x1 because we're sorting it by the value. And we will want it. No, we don't want it reversed. Uh-oh. That's not what I was expecting. What did I mess up on? Why do most of our birds have no spectrograms? Ooh. You know, we never looked at the scores to make sure that everyone had a valid score. Let's check that out. So, bird scores. What was it? We actually need the audio files here. Enumerating Florida birds, and that'll give us the index and then the assets inside. And then how about we keep our score counts as a keep it as a dict, but it's going to have a tuple in it of yeses and nos, essentially. So what are we doing here? Let's get that started again. So we want to know the scores for each one. So yes equals 0, no equals 0. And we gotta say for asset ID and actually asset IDs, not indexes. Scores for that asset ID. And split it, a comma, and we also got a list map int that. There we go. For score in scores if score. That should probably be classification, shouldn't it? if our classification is equal to the index above, I should go and call that bird index just to make it nice and verbose. Okay, if classification equals this. Zero, zero, and that's going to be yes, no. Else the second part of that tuple plus equals 1. Are we still sorting this? Yeah, we'll still sort it. We're going to sort it by yeses. Classification that. I messed up. Key error bird. Asset IDs. Oh. Asset IDs is equal to info audio. Try that. Nope. Info is not defined. That goes right here, actually. No, string indices must be integers. Asset ID index. String indices must be integers. What is the info? Info is bird. That's weird. What am I looking at? Florida birds, bird index, asset IDs. Put this in the wrong place. There we go. So asset IDs is equal to that. Tuple object does not support item assignment. Oh, really? Okay, well, I didn't know I couldn't do that. So let's go back to our yes. 0, no equals 0. Okay. And we'll just say yes is more, and then no is not. Key error. Must map int scores asset ID. Really? It's on its scores? I wonder if this is why all of our writing actually errored out. What if we did this? One, two, three, and then we don't have anything in there for 4. That's weird. So what if we're just gonna try it, right? No go on asset index. Right, yeah, these definitely should not go that high. They should go up to like max of 50, right? So we have some that don't have scores, but it doesn't look anything ridiculous. So I just need to go back and add that to here. Oh, up a little bit. So asset scores is this. Try that. Accept. Continue. See, we couldn't do anything. I'm going to look here real quick just to see if one of our higher birds has make sure that there are scores in there and that I didn't air it out at some point there. Okay, so we do have scores for other birds. So just some sanity checking. This did not go the way that I was originally expecting when starting this video. That makes 2 in a row now, right? So what are we going to do? We're going to go back through to this segment here and run it again. All right, let's see how that works. So I'm just changing something around here so that way we could we could graph these score values. So it's creating these spectrograms still, but I just want to graph the scores and make sure that everything is reasonable. So for this we need JSON and matplotlib. We're going to take this thing here that we've been writing, come over to that right there. Actually, so just to explain this real quick, again, we're getting our JSON file of Florida birds that has the birds by index and all the assets assigned to those birds, or that have been labeled as that index. The scores that we grabbed from using the model and throwing all of our training data at that and predicting the training data from its own model. And here we're creating a bird score count dict. It's going to loop through all those Florida birds, keeping a score of yes and no. Then looping through all the assets for that bird up to the first 50 of them, because that's how many we went through and scored. Okay, looping through all of those and seeing how many are yeses and how many are nos. Yeah, by checking to see the classification count in there, right? How many times does every score for that asset equal this bird? How many times does it not? So create that, and then let's graph it. So for this, what is it going to be? PLT dot, is it a plot? And we have a range of 105. And then here we would have, we're just looking for our yeses, right? So we're going to do I0 for I in bird score count. And that should be sorted, right? If we use a bird score count dot keys, it comes back sorted. Okay. Hey, look at that. Okay. Not too bad. Not too bad. So some birds is going to work better on than others. Right? It's going to predict some birds better than others. Just the way it is for right now. Whatever is number 40. That one's going to be nice. All right. Let's add one other thing to this. Can I do this? Color equals orange. Yep. So blue. And then here we're going to graph our nose. So a lot more no's than yeses, and that's good. It would be nice to improve some of these so that way the ones that are lower counts that we can get some yeses in. We can probably do that if we go back through all of this again and increase the number of files that we're letting go into the model. That would probably really help. Okay, so we're still running this other thing. That's creating the spectrograms for the second iteration here. Looks like we have 1,800 spectrograms created so far. Look at that. Pretty. But now we can expect that some of these are not going to have spectrograms in there. And then look at that, number 40, lots and lots. Just as we would expect, because number 40 has a nice little spike right there. Where's the lower one? See, what's that, around like 38 or so? Yeah, 37, low. 38, low. 33, none. I would expect some from 33, because I don't think that's a 33 value, but it might be. We can always look, all right, like. Oh, yeses and nos. Okay, so that's. Expected smaller numbers there. There's our smaller one, 38. 37. Down to 4. So I guess it's not 0, but it's just close. And then what? There's another one around 20. Yeah, 5. Okay. So it's still rolling. I wonder how far it's gotten. We're on bird 92. So when we started this, it was because I looked at 94 and there was nothing there. So we haven't created 94 yet. I just created 65, but made 92, right? There's some stuff for 92. So we know we are getting through all of our classes now. This isn't erroring out. Yeah. Cool. So stop here and come back whenever it's done again. Okay, so I think we've created our training data. This pool has ended, and I think we now have, still have no specters in 94. No director for 95, uh-oh. Well, we still error it out somewhere. Where was the error? Somewhere on here we should have, well, let's see, 97. Oh, there's our error. Ah, crap. Wait, what? Yeah, okay, so this is coming from Google. Try. Accept. Continue. Wait this time dot sleep. 10 seconds. Try it again. There. And just for sanity's sake, we're going to go ahead and wrap this whole thing in a try catch block. Or try accept. Could not even. What bird are we on? Asset ID. Asset index. It's all backwards, isn't it? Let's do bird index first. That's bird index. Okay. And boom. There we go. Now, one more time, I will set this off to run. Actually, make sure it's saved. I'm pretty sure restarting the kernel saves it, but you know, I don't. So one more time, we're going to loop through all of these birds. I think before it took maybe 20 minutes. 20 minutes, ate some food, came back here, and yeah. Thought it was done. Started the video. It wasn't done yet. So, it's starting. We'll check back in a little while. Alright, let's follow it up here with what will hopefully be finally a quick video today. It looks like we got all the way through. Let's see if we had any errors at the end. No errors. Just some issues sending all the output. So cool. And if we go through and actually look at 97 again, there's a spectrogram for 97, 93, 92, 94. They all have spectrograms. And if we look at all of them, we're just going to recursively list the directory and run WCL, which will count the lines. And we got around 5,400. Cool. So after all that, now we do the TF record part. So just to catch you up in case you're starting right here, we have these spectro files, and these are essentially CSV files. Each one has, 512 times, what was our width that we ended up going with? 196. So each of these files has a spectrogram that's been flattened out into one dimension. And we are going to loop through all of these files here. And write them to TF records, because TF records are great for your training data. They allow the data to already be structured and to where you can read it from the disk really fast. So that way, if you're using like a GPU to train, your bottleneck is not the hard drive. It's not reading this data. It's the processing of it. So when you have a lot of data like this, TF records, they're nice. So what we're doing here is we're going to remove the TF record directory. We're going to make it again. And then we're creating this task called make TF records. Actually, it's a function that we're going to call the task in just a moment. It has a task index, which is really just the, it's one of 16. So we're going to have 16 tasks here. Pretty much we're making 16 TF records. Each one we're randomly going to, keep walking through here. A TF record, we're going to open it up, and it's just one of 16, right? Some random number. It doesn't really matter which one is which. We're going to run all 16 of them. And then we're going to loop through for a range of n classes by max files times 10. I forget why I use max files there. But anyway, that's how many times we're going to go through this. So what's that? That's 105 times 50 times 10. So 105 times 50 times 10. 52,000 times. That's a little ridiculous, I think. I don't think we need that many. Do we? We have 5,000. Yeah, we definitely do not need that many. What if we just do this? We'll go by 5,400. That makes sense, right? We're just going to put this number in here. So we're pretty much looping through one for every one of these spectrogram files. And then every time we get to 100 items, we're printing out some status update. Here we got the class index, which we are randomly selecting from one of our classes, right? So we're just going to pick a class every time that we make an example from random. Then we're going to take all the spectrograms for that class. We're going to randomly choose one of those spectrograms. We're going to come here and parse that data out from a CSV to actually a list of integers or float numbers, not ints. Then here we make a feature dictionary. So this is really what the core data, the core body of a TF record is this feature example. And in this we have two keys, one that we called class, and that's just the class that we have coming in from here, the class that we randomly select. And then we have the spectrogram, which is also a TF train feature. This is a float list though, because we have floats going in. And the value is that spectro that we just parsed out right here. Does that make sense? Good. Here's the example proto, where we're just taking and wrapping that feature up into an example. And then we write it to that TF record file that we created for this task. And when we're done with that loop, we close it. And we're going to do this, 16 times. So that's running. So we should now be ready to train a model with this filtered training data and see how that works.